energy. It's not just this abstract thing, is it? It powers, well, everything we do. That screen you're looking at right now, the car you might drive later, the food you eat, even the water from your tap, it all relies on this incredible, often kind of hidden journey. But how much do we really get about where it actually comes from? How it's transformed and the huge, intricate processes involved. Today, we're going to dive headfirst into your fantastic sources. We're really ripping back the curtain on the fundamental forces, the ancient processes, everything that powers our world. We'll unpack it all, from the tiniest electric charge to like the massive geological stuff that gives us fossil fuels. And we'll even get a glimpse into the maybe surprising future of energy.
Yeah, and what's really great about this kind of deep dive is how we can connect things that seem totally separate. The invisible flow of electrons, ancient swamps, deep earth pressure, it all weaves together. It reveals this really complex, interconnected picture of our global energy landscape. It's about understanding not just what powers us, but the how and the why, and, well, how those choices really shape our present and definitely our future.
Okay, let's start with the basics. We flick switches all day long, right? But honestly, beyond knowing its electrons moving, I'm still a bit hazy.
Yeah.
What is electricity at its absolute core?
Right. So fundamentally, electricity is just the movement of electric charge. Simple as that. Usually it's electrons, and they're moving through something that conducts electricity like a copper wire.
Yeah.
And the force pushing them, that's the electromagnetic force. It's one of the 4 fundamental forces in the universe.
A fundamental force, okay. But turning that force into actual power we can use. That's the clever bit, isn't it?
Mm-hmm.
How do we actually harness it? How do we get those electrons flowing?
That's where electromagnetic induction comes in. It sounds complicated, but the idea is pretty neat. Imagine taking a coil of wire and spinning it inside a magnetic field.
Like in a wind turbine or a dam.
Exactly like that. As that coil spins and cuts through the magnetic field lines, it sort of disturbs them, and that disturbance basically forces the electrons inside the wire to start moving. That movement is your electric current. So a generator, really, it's just converting mechanical energy that's spinning into electrical energy, all using magnets and wire.
Okay, that makes the how much clearer. But then there's the next big question, right? For our wallets, for the planet, how well are we using it once we've made it? What's efficiency here?
Efficiency, in energy terms, is pretty straightforward. It's about how much of the total energy you put into something gets turned into useful work. Like light from a bulb, instead of being wasted, usually wasted as heat.
Ah, the heat thing.
Yeah. And the calculation is simple. It's the useful energy you get out divided by the total energy you put in times 100 to get a percentage. So if you put in, say, 100 joules of energy and you only get 60 joules of actual light out, well, that bulb is 60% efficient, the other 40% is lost, probably as heat.
Let's make that real. Light bulbs, we all use them. What's the efficiency story comparing the main types?
Oh, light bulbs are a perfect example. Those old incandescent bulbs, the ones with the glowing wire.
Yeah, the classic ones.
Terribly inefficient, really bad. Only about 10% of the electricity actually becomes light. A whopping 90%, just heat.
Wow, 90% waste.
Then you had CFLs, the compact fluorescent ones. They were better, maybe 25% efficient at making light, a good step up. But the real game changer, LEDs. Light-emitting diodes.
Right, LEDs are everywhere now.
And for good reason. They're incredibly efficient. We're talking 40, maybe even 50% of the energy becoming light. Plus, they last way, way longer.
So my old incandescent bulbs were basically tiny space heaters that happened to glow a bit. No wonder my grandmother was always yelling about turning lights off.
Exactly. She was literally paying to heat the room with light bulbs. Higher efficiency means less energy wasted, which means, brighter homes for less power, lower energy bills for you, and less demand on the power plants overall. It ripples outwards.
Okay, from electrons zipping around, let's go deep, deep into the Earth's past. Because so much of our power started as, well, ancient life, cooked over millions of years. Let's get into crude oil. How does the Earth actually make something like that? It seems incredible.
It really is. Crude oil is basically liquefied history. It starts with tiny marine organisms. Think plankton, algae, stuff floating in ancient seas millions of years ago. When they died, they sank to the seafloor. And over vast amounts of time, layers and layers of mud and sediment piled on top.
Burying them deep.
Exactly. Burying them and, crucially, protecting them from oxygen so they didn't just rot away. Now, as these layers get deeper, the heat and pressure ramp up. And there's this sweet spot, geologists call it the oil window. It's usually between, say, 2 and 4 kilometers down. The temperature there is roughly 60 to 120 degrees Celsius.
Not super hot, but warm.
Warm enough. In that window, chemical reactions start breaking down the organic matter into this waxy stuff called kerogen. And then with a bit more heat and time, that kerogen transforms into the liquid hydrocarbons we know as crude oil. It's a long, slow cook.
Amazing. So once it's formed way down there, does it just stay put? And how did ancient people even find it without, fancy drills?
Good question. Oil is actually lighter than the water and rock around it, so it tends to migrate upwards. It seeps through porous rock layers, moving up, until maybe it hits a layer it can't get through, an impermeable cap rock.
Ah, like a lid.
Precisely. And that traps the oil, creating a reservoir. That's what we drill into today. But ancient humans, they found it where it naturally seeped all the way to the surface, through cracks or faults in the rock. These natural oil seeps were the first encounter.
So crude oil and natural gas. They both start with those marine critters, right? What's the main geological difference in how they form? Does that affect how we get them out or how they impact things?
Yes, same starting point, buried marine organic stuff. The key difference is really the temperature. Oil forms in that oil window, like we said, 60 to 120 C. Natural gas needs it hotter. It forms deeper in the gas window, which is generally above 120 degrees Celsius. At those higher temperatures, the heavier hydrocarbon molecules that make up oil actually break down further into much lighter, simpler molecules, mostly methane.
The methane, right? CHAs.
That's the one. So, chemically, crude oil is this complex mix of long, heavy, liquid hydrocarbons. Natural gas is mostly just methane, which is, well, a gas at surface temperatures. And yes, these differences absolutely affect everything. Extraction methods, processing, environmental impact. It all stems from those formation conditions.
Do they tend to be found together
Yeah.
or separately?
Both are possible. Often you'll find natural gas sitting on top of oil in a reservoir, like a gas cap, because it's lighter. But you can also find deposits that are just oil or just gas, especially really deep down, where it might be too hot for oil to even exist anymore. You might only find gas.
Okay, let's switch gears. What about coal? Is its origin story completely different from oil and gas?
Quite different, yes. The main thing is the starting material and the environment. Coal comes from land plants. Think huge ferns, trees, all the vegetation in ancient swampy wetlands millions of years ago.
So not marine life?
Nope. Terrestrial plants. This plant matter accumulated in these low oxygen swamps, didn't fully decompose, and slowly turned into peat. Over millions of years, pressure and heat compressed that peat, driving out water and turning it into coal. The key difference in composition is plants are full of cellulose and lignin, these tough, carbon-rich structures that form solid fuel. Marine stuff had more lipids and proteins, leading to liquid and gas.
And you mentioned a specific time. When did most of our really big coal deposits form? And why then?
The Carboniferous period. Around 300 million years ago, that was the absolute prime time for coal formation.
The coal boom.
Exactly. Conditions were perfect. You had vast, widespread tropical wetlands, huge swamp forests covering large parts of the continents. Oxygen levels were also really high then, fueling massive plant growth. But here's the kicker. The fungi and bacteria that are really good at breaking down lignin, that tough, woody part of plants, hadn't fully evolved yet.
Seriously, nothing could eat the wood effectively.
Not like today, no. So dead plants just piled up and up and up, didn't decompose properly, formed massive layers of peat, which eventually became those huge coal seams we mine today. Coal has formed at other times, but never quite on the scale of the Carboniferous. Those deposits are generally much smaller.
Fascinating. And is all coal the same? Or are there different types?
Oh, definitely not the same. There's a ranking system based mainly on how much carbon is in it, which also tells you how much energy it holds. It reflects how much heat and pressure it experienced. You start with peat. It's not even really coal yet, more like a precursor, maybe 50-60% carbon, foggy stuff.
Right.
Then you get lignite, sometimes called brown coal. It's soft, has a lot of moisture, maybe 60-70% carbon, lower energy content. Up from that is subbituminous coal, a bit harder, drier, 70-76% carbon. A lot of this gets used in power plants. Then bituminous coal. This is the classic black, relatively dense coal. 76-86% carbon. It's a real workhorse for electricity and also making steel. And at the top, the highest rank is anthracite. It's hard, shiny, almost metallic looking. Very high carbon, 86 up to 97%. It burns the hottest and the cleanest of all the coals.
So more carbon generally means more energy and cleaner burning.
That's the general rule, yes. Higher rank, more energy packed in, and usually fewer impurities, so it tends to burn a bit cleaner.
Okay, so we know how oil gets cooked up over ages,
Huh.
but how long have we actually been drilling for it, pulling it out of the ground intentionally, especially here in North America?
Well, the game really changed in 1859. That's when Edwin Drake drilled the first commercially successful oil well. Happened in Titusville, Pennsylvania.
1859, wow.
Yeah, that really kicked off the modern petroleum industry as we know it. Before that, people mostly just collected oil from those natural seeps we talked about.
So fast forward to today. A modern oil rig. It's got to chew through a lot of rock. How does it actually work? What's going on inside that massive structure?
It's pretty clever engineering. You've got
Yeah.
the tall derrick, right? The tower structure. That supports everything. Then there's a system, either a rotary table or a top drive, that spins the long drill pipe. And at the very end of that pipe is the drill bit, the part that actually grinds the rock.
Okay, but what happens to all the ground up rock?
Ah, that's where drilling mud comes in. It's not just mud, it's a specially engineered fluid. It gets pumped down the inside of the drill pipe, shoots out through nozzles in the drill bit, and then flows back up the outside of the pipe, carrying all the rock cuttings with it to the surface.
So it cleans the hole.
Cleans the hole, yes, but it does more. It also cools and lubricates the drill bit, helps stabilize the walls of the borehole so they don't collapse, and critically, it provides pressure to control any influx of oil or gas, preventing dangerous blowouts. It's really vital stuff.
Got it. Now, we hear a lot about tar sands or oil sands, especially up in Canada. How different is that stuff from the regular oil, say, pumped in Texas? Is it even the same chemically? What's the deal?
They are very different beasts, actually. Tar sands or oil sands don't contain liquid crude oil like you find in Texas. They contain bitumen.
Bitumen, like asphalt.
Very similar. Bitumen is super thick, sticky, almost solid at room temperature, much heavier and more chemically complex than conventional liquid crude. Getting it out is totally different too. In places like Canada's Athabasca region, if it's near the surface, they literally mine it. Huge shovels, massive trucks digging up the sand.
Like a quarry.
Exactly. If it's deeper, they use methods like steam injection, pumping steam underground to heat the bitumen up enough so it can flow and be pumped out. Both methods are way more energy intensive and unfortunately produce more greenhouse gas emissions per barrel than pumping conventional oil.
And conventional is just pumping liquid.
Pretty much. Conventional oil is trapped in porous rock, usually deeper down, and because it's already liquid, it flows more easily. You drill a well, maybe horizontally now, and pump it out. So yeah, both are hydrocarbons, but tar sands bitumen is much thicker, needs more processing, it's dirtier, and just harder to get at.
Okay, so we've got conventional oil and gas and the sticky tar sands. What about other unconventional gas sources? Things like shale gas, or that stuff called fire ice. Sounds like something from a fantasy novel.
Ah, fire ice does sound dramatic, doesn't it? But yeah, there's a lot of gas locked up in tricky places. Let's break down three main types of unconventional gas. First, coal bed methane CBM. This is methane that's literally trapped inside coal seams, absorbed onto the coal itself.
There's gas hiding in the coal.
Exactly. To get it out, they drill into the coal seam and pump out water. Removing the water lowers the pressure in the seam, and the methane desorbs it releases from the coal and flows up the well. CBM is actually a pretty significant source in places like the US and Australia.
Right.
Second, shale gas. This is gas trapped in super fine-grained rock. Shale, which has very low permeability, the gas can't flow through it easily.
Right, needs help getting out.
Big time. That's where hydraulic fracturing or fracking comes in, usually combined with horizontal drilling. This technology unlocked massive amounts of shale gas, especially here in North America. It's been a real game changer for supply. And third, methane hydrates. That's your fire ice.
Okay, what is it?
It's literally methane gas molecules trapped inside a crystal lattice of water ice. Forms under high pressure and low temperature, mostly found under the ocean floor on continental margins and also in permafrost regions.
And can we use it?
Not yet, really. Recovery is still experimental. People are testing methods like heating it up or reducing the pressure to make the ice structure break down and release the gas. The potential is huge. There might be more energy in methane hydrates than in all other fossil fuels combined, but it's not commercially viable today. Very much a future potential source.
Let's focus on fracking for a second, since it's so key to shale gas and often in the news. What exactly is it, and why is it necessary for these shale rocks?
Right. Fracking hydraulic fracturing is basically a well stimulation technique. It's designed specifically to get oil or natural gas out of rocks like shale that have extremely low permeability. Think of shale like a very dense, tight sponge. The gas is in there, but the pores aren't well connected, so it can't flow out on its own. Fracking creates pathways for it.
How does it do that?
Okay, the process involves drilling a well, often vertically down and then horizontally out for thousands of feet through the shale layer. Then they perforate the well casing, basically punch small holes through the pipe and into the rock using controlled explosive charges. Next comes the frack job itself. They pumped down a mixture, mostly water but also sand, called proppant, and a small amount of chemical additives at extremely high pressure. This pressure is high enough to actually fracture the shale rock around the wellbore.
Cracking the rock underground.
Exactly. Creating a network of tiny fissures. The sand in the fluid gets pushed into these cracks and props them open after the pressure is released. These propped open fractures act like highways, allowing the trapped gas or oil to flow through the shale into the well and up to the surface. Then the fluid is pumped back out and the gas is collected.
That sounds incredibly powerful, and it's obviously unlocked a lot of energy. But what are the main upsides, and what are the big concerns or trade-offs people talk about?
Well, the major benefit has clearly been accessing enormous domestic reserves of natural gas and oil that were previously unreachable. This dramatically increased supply, lowered natural gas prices significantly in North America, and in many places helped displace coal for electricity generation, since gas burns cleaner in terms of air pollutants and key-oro.
Okay, those are big positives. What about the downsides?
There are definitely significant environmental concerns that need careful management. Two key ones stand out. First, the risk of groundwater contamination. If the well casing isn't properly constructed or fails, fracking fluids or methane itself could potentially leak into drinking water aquifers. Improper handling of the wastewater produced is also a risk. Second is induced seismicity, basically, causing small earthquakes. This isn't typically caused by the fracking process itself, but more often by the disposal of the large volumes of wastewater produced. Injecting this wastewater deep underground into disposal wells can sometimes trigger minor quakes on nearby faults.
So it's a complex picture.
Very much so. Fracking has reshaped the energy landscape, boosting supply and lowering costs, but it comes with real environmental risks that require strong regulations, best practices, and ongoing monitoring to manage effectively.
Right, so once we get the crude oil out, whether it's conventional or from tar sands, it's still this thick black stuff. We can't just put that in our cars. How do we get gasoline, jet fuel, diesel, all that stuff out of it?
That's the magic of the refinery. Specifically, a process called fractional distillation. It's based on a simple principle. Different components of crude oil boil at different temperatures.
Okay, so you heat it up.
Exactly. You heat the crude oil to a high temperature, maybe around 350 degrees Celsius, so most of it turns into vapor. Then, this hot mix of vapor and some remaining liquid is pumped into the bottom of a tall vertical distillation tower, often called a fractionating column. Inside this tower are trays or plates at many different levels, and there's a temperature gradient that's hottest at the bottom and gets progressively cooler towards the top.
Like different temperature zones.
Precisely. As the hot vapors rise up the tower, they cool down. When a specific hydrocarbon component reaches a height where the temperature matches its boiling point, it condenses back into a liquid on one of those trays. The heavier molecules have higher boiling points, so they condense lower down in the tower. The lighter molecules have lower boiling points, so they travel higher up before condensing.
Could you walk us through that, like bottom to top, what comes off where?
Sure. At the very bottom, where it's hottest, you get the heaviest stuff that maybe didn't even vaporize fully. This is residue, things like asphalt for roads or fuel oil for ships and industrial furnaces. Boiling points are way up there, over 315 degrees C or 600 degrees Fahrenheit. A bit higher up, you get heavy gas oils like lubricating oils and waxes, boiling maybe 260, 315 degrees C, 500, 600 degrees Fahrenheit. Moving up into the middle section, you get diesel fuel for trucks and buses, and also kerosene, which is refined into jet fuel. Boiling range maybe 150, 260 degrees C, 300 and 500 degrees air.
Okay, getting lighter.
Yep. Higher still, you get gasoline or petrol. This is a mix of hydrocarbons boiling roughly between 40, 150 degrees C, 100, 300 degrees Fair. Huge demand for this fraction, obviously. And right at the very top where it's coolest, you get the lightest fractions. Things like LPG, liquefied petroleum gas, which includes propane and butane used for cooking and heating, and other very light refinery gases used as feedstocks for making plastics and chemicals. These boil below 40 degrees C, 100 degrees air.
Wow, so one tower, multiple products, all separated just by boiling point.
Pretty much. It's a continuous process, constantly separating that complex crude oil mixture into these different fractions that become the fuels and products we rely on every day. It's incredibly efficient at what it does.
Okay, let's zoom back out. Thinking globally now. Who are the major players when it comes to oil? Who's producing the most and who's using the most? I imagine that map has some big implications.
It definitely does, and it's constantly shifting, but some key players tend to stay near the top. Currently, the top four oil producers are roughly the United States, Saudi Arabia, Russia, and Canada.
Okay, U.S. #1 producer now. That's a big change.
Huge change, largely thanks to shale oil.
Yeah.
Now, on the consumption side, the top four users are the United States, China, India, and Japan.
Right, so the U.S. is at the top of both lists.
Yeah.
Interesting. But what about countries like China, India, Japan? Massive consumers, but not top producers. What does that mean for them?
Creates a vulnerability, right? Absolutely. That's a major strategic vulnerability. Countries that consume significantly more oil than they produce are heavily reliant on imports. Their economies become really sensitive to global oil price fluctuations, supply chain disruptions, geopolitical events in producing regions, you name it.
So what can a country in that position do? How do they try to improve their situation?
There are two main pathways, really. One is aggressively pursuing energy efficiency, investing massively in public transport, encouraging electric vehicles, making industries use less energy per unit of output, just using less oil overall. The other pathway is diversifying their energy sources. That means developing domestic alternatives, especially renewables like wind and solar power, but also nuclear, hydro, advanced biofuels, anything to reduce that dependence on imported oil. Both strategies, efficiency and diversification, help improve energy security and insulate their economies from the volatility of the global oil market.
Makes sense. Now, fossil fuels and key oros, always linked to discussions about climate change. How do the big three, coal, oil, natural gas, stack up against each other? Which releases the most key oro for the energy we get?
Yeah, there's a clear ranking there.
Ah.
Per unit of energy produced, coal releases the most carbon dioxide. Oil is in the middle, and natural gas releases the least.
Why is that?
It comes down to their chemical makeup, specifically the ratio of carbon to hydrogen atoms in the fuel. Coal is mostly carbon, so when it burns, almost all of it becomes KERO. Natural gas is mostly methane, a CH. It has 4 hydrogen atoms for every carbon atom. When it burns, you still get CERO, but you also get energy from the hydrogen burning to form water. So less KERO comes out for the same amount of energy release compared to coal. Oil is chemically in between the two.
Okay, so gas is the cleanest of the three in terms of PROs. How has our actual use of each of these changed globally since, say, the 1980s? Have the trends followed that environmental ranking?
The trends are pretty interesting. Since around 1980, global coal use has actually decreased in many developed nations, especially for electricity. Environmental regulations and the rise of cheaper natural gas have driven that. Although globally, its use did rise for a while due to growth in places like China and India, but the trend in many places is now down. Oil use has remained fairly steady, maybe a slight increase overall globally. It's still absolutely dominant in transportation and as a feedstock for industry. Hard to replace there so far. Natural gas usage, though, has increased significantly worldwide. Big time. Especially for electricity generation. Why? Well, it is cleaner burning than coal, and, crucially, the fracking revolution made vast new supplies available and relatively cheap, particularly in North America.
So summing it up, less coal in many places, oil holding steady, and a lot more natural gas.
That's the general picture, yeah. And that shift has slightly reduced the average 2 euro emissions per unit of energy generated globally. But the overall amount of energy we use from fossil fuels is still enormous, so total emissions remain a huge challenge.
That leads right into alternatives. Given the issues with fossil fuels, what about making fuels from something renewable, like algae? Is that science fiction, or can we actually make hydrocarbons from pond scum?
Not science fiction at all. Producing hydrocarbons from algae is a really active area of research and development. It's basically trying to replicate the natural oil-forming process, but, on hyperspeed.
How does it work?
Algae are amazing little biofactories. Many types are naturally rich in lipids, fats, and oils. These are chemically quite similar to the molecules in petroleum. So the basic idea is first you grow the algae, lots of it, usually in open ponds or closed systems called bioreactors. They need sunlight, euros, and some basic nutrients. Then you harvest the algae biomass. You have to get the oil out, which usually involves drying the algae and then using processes like pressing or chemical solvents to extract the lipids. Finally, you take those extracted lipids and convert them into usable fuels. A common process is transesterification, where you react the lipids with an alcohol, like methanol, using a catalyst. This breaks down the lipids and reforms them into molecules that are essentially biodiesel. You can also use other processes to make green gasoline or jet fuel equivalents.
So similar starting point, oily biomass, but way faster.
Exactly. Both start with lipid-rich organic matter. Both end up with long-chain hydrocarbons. But algae grow in weeks or months, not millions of years, and they consume keiko as they grow. So the potential is there for a renewable, potentially carbon-neutral liquid fuel. Still challenges with cost and scale, but it's promising.
Let's circle back to coal for a moment. It's got a long history and often a heavy environmental impact. Can you break down some of the main issues, both from digging it up and burning it, and crucially, what can actually be done? What solutions exist?
Sure, coal definitely presents challenges across its life cycle, but we've also developed ways to mitigate them. For extraction, you have things like mountaintop removal mining, especially in places like Appalachia. It's devastating, literally blows the tops off mountains, destroys forests, buries streams in rubble.
What's the thinks there?
Well, avoiding it altogether through alternative mining methods is key, but also stricter regulations requiring much better, more complete reclamation, restoring the land with native plants afterwards. Another big extraction issue is acid mine drainage. Exposed rock surfaces in mines react with air and water, producing sulfuric acid that leaches toxic heavy metals into rivers and streams, killing aquatic life.
How do you stop that?
You can treat the acidic water runoff, often using lime to neutralize the acidity. Also, building engineered wetlands can help filter out the heavy metals naturally before the water rejoins the ecosystem. Then you get to combustion. Burning coal releases a cocktail of air pollutants. Sulfur dioxide, SO, causes acid rain. Nitrogen oxides, NO, form smog. And tiny particulate matter is really bad for respiratory health.
And the solutions for the smokestack?
Technology. Power plants install scrubbers or flue gas desulfurization systems to remove SO. They use electrostatic precipitators or fabric filters to capture particulate matter. Technologies also exist to reduce NO formation. Of course, the elephant in the room is carbon dioxide, CO emissions. Coal is the most carbon-intensive fossil fuel, a major driver of climate change.
What can be done about the CRO?
Improving the efficiency of coal plants helps getting more energy per ton burned. Switching to lower carbon fuels like natural gas or renewables is obviously a major solution. And then there's carbon capture and storage, CCS technologies, designed to capture COs from the smokestack and store it underground, preventing it from reaching the atmosphere. It's technically challenging and expensive, but being developed. Finally, after burning, you've got coal ash. This residue contains toxic elements like arsenic, mercury, lead. If it's not managed properly in disposal ponds or landfills, these can leach into groundwater or spill, causing major contamination.
So managing the waste is critical too.
Absolutely. The push is towards storing it in lined, monitored landfills to prevent leaching, and also finding beneficial reuses for the ash, like incorporating it into concrete and building materials. So yeah, lots of impacts, but also a lot of engineering solutions developed over decades to try and minimize them.
That's a comprehensive list. Can we focus specifically on making coal burn cleaner, especially tackling the sulfur? You mentioned pyrite earlier.
Yeah.
What are some specific techniques?
Right. Dealing with sulfur, often present as iron pyrite, Fe in the coal, is crucial for reducing acid rain and air pollution. There are ways to tackle it before, during, and after burning. 1. Coal washing, pre-combustion. This happens before the coal even gets to the power plant.
Washing it.
Essentially, yes. You crush the coal and mix it with water or another liquid. Pyrite is much denser than coal. So in this slurry, the heavy pyrite particles sink, while the lighter coal particles float or stay suspended. You can then separate them.
Can you physically remove some sulfur beforehand?
Exactly. You take out a good chunk of the mineral sulfur before it even enters the furnace. Less sulfur in means less SO euros. 2. Fluidized bed combustion, FBC, during combustion. This changes how you burn the coal.
How does that work?
Instead of burning big lumps on a grate, you inject finely crushed coal mixed with limestone, calcium carbonate, kako into a combustion chamber. Hot air blown from underneath suspends this mixture, making it behave like a bubbling fluid, hence fluidized bed. The key is the limestone reacts directly with the sulfur dioxide as it's formed during combustion. The SO combines with the calcium carbonate to form solid calcium sulfate, gypsum, which is then removed along with the ash. It captures the sulfur right in the furnace.
Clever, capturing it mid-burn.
Yep. And it also allows burning at lower temperatures, which reduces the formation of nitrogen oxides, another pollutant. 3. Flue gas desulfurization scrubbers, post-combustion. This is the cleanup crew after the coal has burned.
Like filtering the smoke.
Pretty much. The flue gases, the exhaust smoke, are passed through a device, typically a large tower, where they're sprayed with a slurry of water and limestone, or lime. Chemical reactions occur in the spray, capturing the sulfur dioxide gas and converting it into a solid byproduct, usually synthetic gypsum, which can sometimes be sold for things like wallboard.
And this is effective.
Very effective. Modern scrubbers can remove 90% or even more of the SO from the flue gas before it goes up the chimney.
So wash it before, capture it during with FBC, or scrub it after. 3 different strategies targeting that sulfur.
Exactly. Each approach helps tackle the SO pollution that comes primarily from the sulfur locked in minerals like pyrite within the coal itself, making coal use significantly less damaging to air quality than it otherwise would be. Tag, outro.
Well, so after all that, from the fundamental push of electrons to ancient swamps, deep earth pressures, drilling miles down, cracking rock, distilling crude, and even thinking about algae, this deep dive has really laid bare the incredible complexity, the ingenuity, and just the sheer scale of how we power our lives, hasn't it?
It really has, and I think understanding these things, the basic science, the geology, the technologies, both old and new, it's just so crucial. It's the foundation for making sense of the energy debates, the choices we face, the whole ongoing global conversation about our energy future.
Yeah, I hope this dive has left you, our listeners, not just with more facts, but maybe with a new kind of appreciation for these hidden journeys, the energy that's humming all around us.
Absolutely. And maybe a final thought to leave folks with, as our global appetite for energy just keeps growing, how do we balance what we know about our deep geological past, these resources formed over millions of years, with the urgent need for innovation and the choices we must make for a sustainable future? That tension is really shaping everything.